Hello, class. Welcome to this last video for this week. And this video I have titled just Definite Integrals and Common Sense. And basically all I'm doing here is trying to give you an idea of how to think about the values of these answers to sense if your answer is reasonable or not. Which is something throughout this semester and this year I've been doing, is sort of thinking about this. And so you've probably gotten very used to this idea of, hey, if you see a point and you look at the graph and the x and y coordinate aren't the right sign, you know something has gone wrong. Or if the slope is not right, you know something has gone wrong, or whatever. And so you've gotten very good at reading off derivatives and sort of checking your answer for various problems in very plausible ways. And I want to talk about how you can think about that in terms of thinking about integrals. Okay. So I mentioned briefly in passing the idea of this integral last time, the integral from 0 to pi of sine of x. Okay, so that would correspond to the area under one hill of a sine graph, if you want, or whatever you want to call this. Okay, so it would correspond to this area. Okay. Now, for this week, we can't do this integral. But we can say an awful lot about this so that next week when we do this integral, we can check our answer and see if it's in the range that we expect. Okay. So this integral we know represents the area under this thing. It's the area bounded by this thing that looks kind of sort of like a semicircle. It's not quite a semicircle. But I can definitely say how big this thing is. It is not totally unknowable. I can convince you, and I hope I will convince you by the end of this video, the area here is definitely not 1,000. Okay. In fact, here's what I can do. I can go ahead and draw a box around this area. Okay. So in black, that's the value of the integral. Okay, so black area equals integral. Okay. But all of the black area is inside this red rectangle. And so what that means is that the black area, which again, I don't know what it is, but it's definitely less than the red rectangle area. And the area of the red rectangle I can calculate. Okay. Well, what's the width? Well, it goes from 0 to pi. So it is pi wide. And what's the height? Well, this is the height of a sine graph. So this point here, actually, the peak here is at pi over 2 comma 1. So that means that this is 1 high. And so the area here is pi times 1, which is just pi. Okay. Now, what I want you to take away from this is that I can fit the entire black area inside a rectangle of area pi and have some stuff left over. So actually the black area, it must be appreciably less than the area of the rectangle, which is pi. So my conclusion from this picture is that definitely this area, it's less than pi. Now, if you look at this and believe my picture, my graph here is at all accurate, where there's these huge gaping white spaces here on the side, then you might say, okay, well, I'm pretty sure it's less than 3, or maybe even you can convince yourself it's probably less than 2.5, however you like. But definitely it's less than pi, and so if you got an answer that was like 12 when you did this, you know something has gone wrong. So again, you have this intuition of sort of like, how big could this area be? Okay. just before I wrap up, I want to point out you can actually do the opposite of what we just did as well. So here, I found a shape that I knew the area of that contained the area, and so that told me, okay, the black area is less than the area of the red thing. I can do exactly the opposite too. I can find a shape whose area I know that's contained in the area. And so in this case, I'm going to draw us in a triangle. Okay. And so this triangle here, the area of this triangle is contained entirely within the area that I labeled as the black area here in this previous graph. And so this blue area, it's less than the black area. Okay. What is this blue area? Well, it's pi wide, and it is still 1 high, because I'm still grabbing this from the highest point on a sine graph. And so the blue area, keep in mind that's a triangle, so it is 1/2 of pi times 1, which is to say the blue area is pi over 2. And so that pi over 2, that's actually less than the area of the black region from before that's represented by the definite integral. And so, in fact, we've shown that the integral's value is actually somewhere north of pi over 2. And so pi over 2, if you think about it, it's about 1.5. And so we've got the value of this integral narrowed down to a region between 1.5 or so and 3 or so, from just this little sort of eyeballing it and thinking about areas we know. All right. Next week, what are we going to do? We're going to talk about why on earth this whole thing with areas gets the name integral, which is the same name that this whole thing with derivatives got. And so, in other words, we're going to connect the idea of antiderivatives with the idea of areas using something that is called the fundamental theorem of calculus. And so you might guess from the name that it turns out to be rather important. So we're going to talk about the fundamental theorem of calculus, and we're going to actually calculate not only the area under the sine graph, but also the area of lots of other things that we'll do. But until next week, be well.